Good morning, everybody, and welcome back from spring break. Hope you guys had a wonderful break. Praying everybody made it back safely. You guys had some rest and some great time with family and with friends there. Just want to review, you guys only have, I think if I've got this right, 6 more weeks of classes as seniors. So that's pretty crazy that we're coming right up on the end of, really close to the end of the semester, the end of the school year here. As a review for this week, this is a fairly normal week. We've got a Monday, Wednesday, Thursday lecture. We've got a quiz on Thursday, and I'll talk a little bit more about that on Wednesday. Just to kind of review where we're at in terms of material, right before the end of spring break, we started to talk about integration techniques. We reviewed the ones that we've gone through so far. So just as kind of a recap. So our integration techniques, kind of our steps to integrate. One of the things we talked about is if we have a rule to apply it immediately to an integral. Otherwise, we're going to try to do something to the integral to get it to be easier so that we can then apply a rule. And one of those steps is simply to simplify. Okay, so we simplify. That's if we see that we can multiply stuff out, if we can divide stuff out, if there's a way to factor and cancel, things like that. Those are things that we talked about last time. Another technique that we have is substitution. And in substitution, one of the things that we look for is we look for composition or the du, something in there is the derivative of something else, right? So we're actually, and then what you do is you let u equal that inner function if you see a composition there. We're actually going to, in chapter 7, going to develop a long list, there's probably going to be about 6 or 7 things on this list that are integration techniques. And with each one of those techniques, there's going to be something that you're looking for, and then something like an initial step that you take to do that technique. So we've got the technique, what you're looking for in the integral in order to do the technique, and then how you actually implement the technique. Now, the order of this is actually going to end up being important because the things that we're going to see later are going to be techniques that are going to turn the integral into something that we're going to do something earlier with. So we might have a technique like the one that we're going to see today that turns the integral into something else, and then from that we're going to do substitution, and we're going to get it in something else, and then we can apply our rules. So it's going to be pretty important that you're going to understand what order these go in, because we're always going to be kind of pointing back to previous techniques. And it's important that you understand what you're looking for to apply these integration techniques. Okay. If there's time at the end today, you'll have a chance to ask Ms. Barabo some questions about the material from 5.10. That's the hyperbolic trig functions. Those probably shouldn't have been too bad. And the review problems from section 7.1. Okay. And again, our motivation for we're doing chapter 7 first before we do chapter 6, because we want these techniques in order to be able to apply them in chapter 6. Okay, so the section that we're going to be talking about today is actually 7.2, that's called integration by parts. And this is going to be our next integration technique. This is going to be technique number 3 that's going to show up over there. So when we review this on Wednesday, I'll add this to that list. Integration by parts is also sometimes abbreviated IBP, integration by parts, IBP. Okay. And this is going to be motivated by, just like substitution was kind of the inverse of the chain rule, so it came from composition, this is going to be the reverse of the product rule. So this is trying to reverse the product rule. Okay, so here we're trying to reverse the product rule. So what we're going to do to get this technique is we're going to start with the product rule. We're going to reverse it and introduce some notation. And then you're going to see what it is that we're doing with some examples. Okay, so first of all, let's recall the product rule. So the way the product rule works is it says that the derivative of f times g is the derivative, let me make sure I get the order here right for how I want to set this up. Derivative of the first times the second plus the first times the derivative of the second. It doesn't actually matter what order you write these in, but I want to be consistent with the notation that we're eventually going to use. So the derivative of f times g is the derivative of the first times the second plus the first times derivative of the second. That should not be mysterious. So that means, so if we integrate everything, the integral of the derivative is just the function. So if we were to apply an integral here and apply an integral to the right side as well, we would get that f times g is the integral of f prime times g plus the integral of f times g prime. Okay? With me so far? So we just integrated that whole equation. And now I'm going to take this part and put it on the other side. Now, I want an equation for this, so what I'm going to do is, rather than write this minus this equals that, I'm going to flip them. But the integral of f times g prime is f times g minus this integral. So f times g minus the integral of f prime times g. Okay? Okay. So there's actually going to be two ways that we're going to write this. One way that we can write this equation is with f and g. And basically the idea is, if I have an integral that has a product in it, there's going to be a way to turn that into, there's going to be some function here, but there's going to be a way to turn that into a different integral with a different product. And if I do this right, this different product is an easier integral than the original one that I started with. And I'll show you what I mean by that later. I'll give you a couple examples, okay? Now this is one notation, so we call this technique integration by parts. Now, there's a notation that's very famous, and it's very easy to use in the situation where you're using integration by parts. You let this function right here, we call that function u, and we call this part of the integral dv. Okay, and if that is dv, so we're just basically naming something u and something v. So if this part is dv, then v is going to be the function g. Notice if I differentiate, if I take the differential, I get dv equals the derivative of g times dx. And du here is going to be f prime times dx. So another way to state this equation with u's and v's is that f is u, so the integral of u times dv equals f times g is u times v, so u times v minus the integral f prime dx, so this part right here is du, and g is v. So this is another way to state that integration by parts equation. the integral of u dv equals u times v minus the integral of v du. And again, the idea is if I have a product, if I start with a product in my integral, I use this technique, and I'll show you how to use it, to change this into a different integral with a different product, but hopefully that product is an easier product than the original one that I was working with, okay? Okay, so that's a lot of words, but let's try this with a couple of examples. Let's see how this actually works here. So let's start with the integral of x e to the x dx. Okay, the integral of x e to the x dx. Now I want you to notice one thing here. First of all, I have a product. That is a key thing here that tells me I need to do integration by parts. When you see products, many, many times you're going to end up doing integration by parts. Okay. Now what I'm going to do is I'm going to think of this as my u function and this as my dv function. Now you might wonder, how did I come up with x being the u function and the other one being the dv function? I'm not going to explain that right now. I want to get to that later. You'll see why I choose what I choose. But I'm going to let u equal this first function x, and dv is going to be e to the x dx. Okay. So now what I need to compute is what du is and what v is. Okay. Now if u is x, then du is dx. So that's easy. V, if dv is e to the x dx, then the original function v is just e to the x, right? If I define dv this way, then the original function v has to be e to the x. So according to my formula down here, this integral, in other words, u dv, the integral of u dv equals, so what I'm supposed to do is I'm supposed to take u times v, so I take the product of these two, so that's x e to the x, minus the integral of v, which is e to the x, du, which is dx. Okay. So using this formula that we developed from kind of reversing the product rule, I turned this integral into a function minus this integral. Now what I want to point out here is that this integral is a whole lot easier to work with than that integral. And that's the point of doing integration by parts. We turn a harder integral into an easier integral. And in fact, I have a rule for that integral. So that integral I can just do now. Okay, that's just e to the x, and then I need a plus c there at the end. So that is my answer. And if you actually differentiate the answer, let's just do a derivative real quick so you can see this. Notice that if I differentiated that, my answer here, okay, I'd have to use the product rule right here. So I'd have derivative of the first times the second plus the first times the derivative of the second minus e to the x, derivative of e to the x is just e to the x, and then derivative of c is 0. And notice that this e to the x and this e to the x cancels, and I get my original answer, which is what should happen. Okay, so the point here, integration by parts takes an integral that has a product, and it spits out some function minus another integral that should be a better product. Okay? Now I haven't explained how did I know to have u be this and dv be this. I'm not going to get into that yet. Okay? Let me do let me do a couple of other examples, and then having those examples on the board, I want to show you why I picked what I picked, okay? But I just want to show you how this works. So let me, in order to do this, I'm going to copy this formula up here. Okay, let's try a couple of other examples, and then I want you to see why I chose what I chose, okay? So let's do x sine x dx. Okay? So again, I've got a product here, so that product is going to be an indication that a light should go off, and I think, oh, product rule, integration by parts. Okay, what I'm going to do, and again, I'll explain this later, I'm going to let u equal this x part, and I'm going to let dv be the other part. dv is going to be sine of x dx. Okay, so then du is just going to be dx. Okay, that would be this differential here. And then the function that I would differentiate to get sine would be negative cosine, right? Right? The function that I would need to differentiate to get sine would be negative cosine. So v is going to be the function negative cosine. So this integral, according to this formula, I've got u dv. This integral equals u times v, that's going to be negative x cosine x, minus the integral of v du. Already got that? So I just use this formula, u times v minus the integral of v du. Okay, so minus minus is a plus, and you'll notice that the function that differentiates to cosine is the sine function, right? Plus plus, minus minus gives me plus. Function that differentiates to cosine is sine. And I just throw my plus c on at the end. And if you differentiate this, just like we did that one, you'll see this ends up differentiating back to give me a nice x sine x. Some stuff cancels out, okay? Let me do another example here. So again, one thing I want to emphasize, integration by parts does not solve the integral. It turns a harder integral into an easier integral. And usually the sign that you're going the right direction is if you get an integral that's easier, you're doing the right thing. Okay, I'll show you an example where that doesn't happen later. But let's take a look at one more example before we start doing some weird things. Okay, so I've got this product, x times natural log x, inside the integral. What do I do? Okay, well, what I'm going to do is actually I'm going to let this be my u. I'm going to let u be the natural log of x. And again, I'm not going to explain why yet. I want you to get used to using, if I tell you what the u and the v are, I want you to get used to doing the technique, and then we're gonna what we're gonna do is we're gonna try messing around with it and seeing what happens if you do it wrong, and then how do we know which one to do. So I'm gonna let this natural log of x be u, and so my dv is gonna be the rest, so it's gonna be x dx. So now let's compute what the du is going to be. Du is 1 over x dx. And v is going to be 1/2 x squared. Okay, 1/2 x squared is going to differentiate down to x, so that will work for me. Okay, so what I'm going to do is I'm going to, according to my formula, here's my dv, u dv, the integral of that is going to be u times v, so it's going to be 1/2 x squared natural log of x minus the integral of v du. Okay, my du is 1/x dx. Now what I want you to notice here, let's just rewrite that first term. Let's pull out the 1/2. X squared times 1/x is just x. So notice that this integral is so much better than this integral. It's so much better. Okay, in fact, this is a very easy integral for me to do. So this is just 1/2 x squared natural log x minus the antiderivative of x is going to be 1/2 x squared. So that 1/2 and this 1/2 is going to give me 1/4 x squared plus my constant. Okay? Does that make sense? All right. So now let's go back and ask the question, why did we pick the u and dv the way that we did? Okay, hopefully you're starting to see this technique happen where I've got a product and I turn that integral into another integral that's simpler. A product, and I turn that integral into another integral that's simpler. What happens if we pick the other way? Okay, let's go to this problem right here. Okay, I'm going to work this same problem right here, and I want you to see what happens. So let's take x e to the x dx, and let's pick the u and dv differently, and let's see what happens. Okay, instead of x being the u, let's let the e to the x be the u. So let's let u equal e to the x, and then the dv is going to be the rest of this. Okay. So dv is going to be x dx. So then my du is just e to the x dx. And what would v be? Okay, v is going to be, the antiderivative of x is going to be 1/2 x squared. You may think, one note that I don't think I made clear, you don't need a plus c here because you just need some antiderivative. We don't need the general one here, okay? So according to my formula here, this integral is going to be u times v, so it's going to be 1/2 x squared e to the x minus the integral of v du, so 1/2 x squared e to the x dx. Now I can pull that 1/2 out of the integral. But what do you notice about this integral compared to now the new integral that I need to do? Which is easier? Notice that this one's actually worse, right? I don't know how to do this one any more than I know how to do that one. It's actually worse because there's an x squared there, whereas there was an x over here. Compare that to what happened before. I had an x e to the x, and it became just e to the x. That's a lot easier, okay? So one rule of thumb is that whatever you try to pick for the u and the dv, if you do some work and you get to a place where the integral is harder or the same difficulty, that may mean that you're going the wrong direction. You may want to switch them. Okay? So notice that same thing would have happened here if I let u equal the sine and dv be the x. Du would end up being cosine, but this thing would turn into a 1/2 x squared, and I'd get a 1/2 x squared here with my cosine, which would be a lot worse integral than the one that I'm dealing with here. Okay? So same concept here. If I picked it wrong, the integral that I would get would be worse than the one that I started with, comparing this one and this one here. Okay. Now looking at this, one of the motivations here is that, so, and this is kind of the summary, the thing that tells you what should you pick and what shouldn't you pick. Notice that working with natural log is awful. Natural log is not a fun function to work with. Okay? But working with its derivative is actually really nice. 1 over x is a very nice function. Natural log is an awful function. So many times when you find a function inside your integral that is awful to work with, but its derivative is nice to work with, then usually you make that function u because you're going to differentiate it and make it the du. You have to keep in mind, though, that whatever is left over, in this case the x, you're going to have to be willing to work with its integral. So we differentiated natural log and we got to 1 over x, but we had to integrate x to get 1/2 x squared. So if working with this combination is better than working with this combination, great. You're picking the right direction. Flipping it around the other way, if that's worse, then you're probably going the wrong direction. Okay. All right. Let me give you another let's take maybe another example here. Yeah. Okay, let's do another example. So let's take the integral of x cubed times the natural log of x. Right? Okay. One of the things that should immediately come to my mind is this function is hard. So number one, I have a product, which tells me I probably want to do integration by parts. The second thing I notice is that natural log is hard to work with, but its derivative is nice. So the first thing that comes to my mind is to let u equal the natural log, and then du would be 1 over x, okay, which would be a lot easier to work with. So if u is this part, if that's my u, then the rest of this has to be the dv. Okay, so dv would end up being x cubed times dx. And that would mean that v would have to be the antiderivative of that, 1/4 x to the 4th. So now I have to figure out, is working with an integral of that's this product better than working with an integral that's this product? So let's take a look. So the integral of u dv is supposed to be u times v, so 1/4 x to the 4th, natural log of x, minus the integral of v du. So I just substitute back in v and du. So cleaning that up a little bit by pulling out the 1/4, x to the 4th times 1 over x is x cubed. Now I ask myself, is this integral better than the original one? Yes, it's much better than the original one. In fact, I can just do it. And what I get is 1/4 x to the 4th there. Okay, and I could rewrite this as 1/16 if I wanted, but the point is that is now an integral that I'm able to do. Okay, does that make sense? Okay. Let's do another example here. Let's try the integral of x times arctangent of x. Okay, so again, I see a product here. So I'm motivated to think, okay, maybe integration by parts. And I also notice that arctangent is just like with natural log. Arctangent is one of those functions that if I can work with it, that's going to be hard. But if I can work with its derivative, so if u equals arctangent, the derivative of arctangent is 1 over 1 plus x squared, which is actually a whole lot nicer function than arctangent. Arctangent seems to be this mysterious function. But 1 over 1 plus x squared is pretty nice. Okay, but if I do that, then dv has to be the rest of this. So x dx, so that means v is going to be 1/2 x squared. So let's check and see what happens if we do this substitution. If we substitute this in, if we do integration by parts this way. So my integral is going to be u times v, 1/2 x squared arctangent x, minus the integral of v du. In other words, let's pull out that 1/2. I've got x squared over 1 plus x squared dx. Okay? Now the question I have to ask myself is this integral better than this one? Well, this one doesn't have an arctangent, so it's almost automatically better than that one. Okay? In fact, that should remind you of a simplification technique for how to do this integral. Do you remember what we would do at that point to do that integral? We actually know how to do it. What we would do is we would actually do long division, right? I've got an x squared. Notice the power of the top is greater than or equal to the power of the bottom. So I'm going to take x squared and divide x squared plus 1 into it, and I need one of those, right? And if I subtract, I'm left with -1 left over. So in other words, this integral becomes, it's actually the integral of 1 minus, and here's the remainder, 1 over x squared plus 1, or 1 plus x squared. Now notice, we used another technique, and the question now is this integral simpler than this one? Yes, because I know how to do this. Right? The integral of 1 is just x, so this is just 1/2 x, plus, the minus minus is plus 1/2. The integral of that is just what? Arctangent. And we're done. Okay, so you see, the product tells me integration by parts is probably the direction I want to go. And the check is, did I get an integral that's simpler than the one I started with? And then from there, I go back to my other techniques that I have previously in the list to see, is there a way that I can make this even simpler? Okay? So that's the basic idea of integration by parts. So let me give you 5 minutes here. Take a 5-minute break. And then you can pause the video here. And when you come back, what I'm going to do, we're going to modify this just a little bit. And then on Wednesday, when we're going to come back and we're going to do integration by parts again, we're going to modify it further. We're going to see a few other kind of intricacies that can come here. Okay, so go ahead and pause the video. Okay, welcome back. So, to see what I'm about, integration by parts, again, is motivated by products. To see, there's another type of thing that will show up. And to see what we need to do here, let me give you an example. So let's take a look at x squared e to the x dx. Now we looked at x e to the x dx. Here we're looking at x squared e to the x dx. Okay. Now for me, when I look at this, again, I see product. So product tells me integration by parts. Okay. And I'm going to let u equal x squared and dv equal the rest of it. Okay, so this is going to be my u, and then this is going to be my dv. The reason is, in my head, I'm thinking that when I differentiate, the x squared becomes basically an x, which is better than x squared. It's not as complicated. But when I integrate e to the x, it's just e to the x, so it stays the same. So this integral is going to be more complicated. The new integral is going to be less complicated because I just have an x and an e to the x. Okay. So notice that if I follow my rule here, I've got u times v, x squared e to the x, minus the integral of v du. So I clean that up a little bit. X squared e to the x minus 2 times the integral of x e to the x. Now we should always step back and ask ourselves, did it get better? If it didn't get better, we're doing something wrong. Did this get better? Now notice I started with x squared e to the x, now I have x e to the x. So it is better, but we're not done. And this motivates a comment that I want to make here, is that sometimes you may have to do integration by parts multiple times. Kind of like sometimes you may have to do substitution a couple of times. So here we picked the right thing, we just need to keep going. So now I'm going to let u equal this part x, and dv be the rest of it again, e to the x dx. So my du is just dx, and my v is, the antiderivative of e to the x is just e to the x. So, here I'm going to ask you to please use parentheses. This integral right here, again I'm going to use parentheses and then later multiply out, is going to be u times v, so x e to the x, minus the integral of v e to the x, times du, which is just dx. Okay? So, I've got x squared e to the x minus 2x e to the x plus 2 times this integral, and that integral is very easy for me to do, it's just e to the x. Plus 2 to the x, and don't forget your plus c. Okay? So again, my integral gets better, but I may need to do integration by parts multiple times. And so that's kind of one of the things that I'm pointing out here, is that you may end up having to do this technique several different times. All right? Let's take a look at another example kind of like that. All right. Let's look at x squared times cosine x. All right. So again, product here tells me, oh, probably integration by parts. And that x squared, if an x squared wasn't there, I could do this really well And I like working with the derivative of x squared. And the integral of cosine is not too bad. The integral of cosine is sine, so it's about the same difficulty level. So I'm going to let u equal the x squared, and the dv be cosine, because the derivative here is nicer. The derivative of x squared is 2x. The integral of v, the integral of dv, the integral of cosine is pretty easy to work with. It's just sine. So what we get here is u times v, x squared sine x, minus the integral of v du. So sine x times 2x dx. And if we clean that up, then, sorry, my computer shut off here. Now we've got an integral, and we compare this. We compare the second integral to the first. Notice that I have an x times a sine x. Here I have an x squared times a cosine. This is better. So we're going the right direction, but we're not quite at a place where I can do it yet. So again, I've got to let u equal x and dv equal sine. Okay, du is going to be dx, and then v is going to be negative cosine, just like we did earlier. So again, using parentheses, please be careful not to do all of this in your head. We've got sine x squared times sine x minus 2 times u times v is negative x cosine x minus the integral of v du. Okay, and if you start doing all of this in your head, you're going to lose all those negative signs. So please be careful. All right, let's clean this up a little bit. We've got x squared sine x plus 2x cosine x. We've got minus 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 is minus 2 integral of cosine. And the antiderivative of cosine is sine. So that is going to be minus 2 sine x. Again, plus c. Okay. So the moral of the story is we may need to do integration by parts multiple times, depending on... Now, you can imagine what would have happened if this was x to the 5th e to the x. Yeah, that's not going to be fun. You can do it, but it's going to take a little while. You'd actually have to do integration by parts 5 times, which sounds not so fun, but the point is, before we couldn't have done that. We didn't have a way to do x to the 5th e to the x. We just had no way. Now at least we have a way. It may take a little while, but we do have a way to do it. All right? So go ahead and give that homework a try, and you should have some extra time here. If you have some further questions on the homework that's due today, you're welcome to ask Ms. Barabell about that as well. Have a great rest of the day, and I will see you on Wednesday.